Imagine a place where the known laws of physics no longer apply, where time may cease to exist, and space folds in on itself. A domain so foreign and extreme that our current understanding of reality begins to crumble the moment we approach it. This isn't the plot of a science fiction novel, it's the actual frontier of modern cosmology, a realm filled with cosmic anomalies that stretch the boundaries of human comprehension and challenge everything we think we know about the universe. In the vast darkness of space, beyond the reach of even our most powerful telescopes, lie phenomena so strange and unpredictable that they seem to mock the elegance of Newton's mechanics and the certainty of Einstein's relativity. Consider the dark matter that holds galaxies together with an invisible grip, yet refuses to interact with light or normal matter in any detectable way, or the dark energy that accelerates the expansion of the universe, countering the pull of gravity without offering us a clue to its true nature. Then there are black holes, those monstrous entities born from the death of massive stars, which bend space-time so intensely that not even light can escape their grasp, yet somehow emit powerful jets of energy, and may even form bridges to other universes through hypothetical wormholes. These aren't isolated mysteries, they're interconnected, woven into the very structure of the cosmos, hinting at a deeper, underlying order or chaos that eludes even our most advanced equations. Quantum mechanics, with its probabilistic haze and particle wave duality, seems to whisper a different truth than the smooth, continuous curves of general relativity. And in the violent birth of the universe, the Big Bang, both theories collide, failing to produce a coherent explanation of how everything came into being. Why does the universe exist at all? Why does it appear fine-tuned for life, with constants that seem almost too perfect to be the result of chance? Could it be that we are just one bubble in an infinite multiverse, where every possibility plays out in a different dimension, and the laws of physics themselves are local quirks rather than universal truths? As we send satellites beyond the heliosphere and peer deeper into the cosmic microwave background, we are not just mapping stars or measuring radiation, we are decoding the ancient message of existence, one that predates Earth, the Sunday, and even the atoms that make up our bodies. And the more we learn, the more questions arise. Is time a fundamental property of the universe, or merely an illusion created by consciousness? Are black holes really gateways to other dimensions, or the graveyards of information? Can the universe be simulated? And if so, what does that make us? The search for answers is not just a scientific endeavor, but a philosophical odyssey, one that demands we look beyond traditional paradigms and embrace the possibility that reality is far stranger than fiction. The stakes are nothing less than the nature of reality itself, and in this vast arena of cosmic enigmas, we find ourselves both humbled and inspired, driven by an insatiable curiosity that no telescope, collider, or computer can fully satisfy. Yet, we continue, because to understand the universe is to understand ourselves, our origins, our future, and the delicate, improbable existence we call live suspended between galaxies, within a speck of matter, on the edge of eternity. In the earliest days of human civilization, the night sky was a canvas of mystery and wonder. Ancient peoples gazed upward in awe, creating myths and legends to explain the movement of stars and planets, interpreting celestial events as messages from the gods. The Babylonians, Egyptians, and Chinese were among the first to systematically observe the heavens, using rudimentary tools to track lunar phases, eclipses, and the motions of celestial bodies. Their observations laid the groundwork for early astronomy. But it wasn't until ancient Greece that a more philosophical and mathematical approach emerged. Thinkers like Pythagoras and Plato speculated on the harmony of the cosmos, while Aristotle posited a geocentric model of the universe, placing Earth immobile at the center, surrounded by concentric spheres of stars and planets. This Earth-centered view, though fundamentally flawed, dominated scientific thought for centuries, codified by Ptolemy in the 2nd century CE in his Almagest, which became the authoritative astronomical text of the Western and Islamic worlds for over 1,000 years. During the Islamic Golden Age, scholars like Al-Battani, Al-Hazen, and Avicenna preserved and expanded upon Greek astronomical knowledge, refining star charts and developing early methods of trigonometry to aid in celestial calculations. Their work would later flow back into Europe through translations, helping spark the scientific revival of the Renaissance. One of the most pivotal shifts in our understanding of the universe came in the 16th century when Nicolaus Copernicus proposed a heliocentric model, suggesting that the Earth and other planets revolved around the Sun. Though controversial and counter to both scientific orthodoxy and religious doctrine, his ideas gained traction thanks to the observational confirmations provided by Galileo Galilei, who in the early 1600s used a telescope to discover moons orbiting Jupiter and the phases of Venus, clear evidence that not all celestial bodies revolved around the Earth. These observations, along with Johannes Kepler's laws of planetary motion and Isaac Newton's formulation of universal gravitation, marked the birth of classical mechanics and revolutionized our understanding of the cosmos, replacing mystical explanations with predictive, empirical science. The Enlightenment and subsequent Industrial Revolution further propelled astronomy forward, enabling the construction of more powerful telescopes and the accumulation of more precise data. By the 19th century, astronomers like William Herschel had discovered Uranus, cataloged thousands of nebulae, and even speculated on the existence of other galaxies. Yet it wasn't until the 20th century that our conception of the universe truly transformed on a cosmic scale. In 1915, Albert Einstein introduced his theory of general relativity, which described gravity not as a force, but as the warping of space-time by mass and energy. This radical reimagining of gravity laid the theoretical foundation for modern cosmology, allowing scientists to explore dynamic models of the universe. Just a few years later, Edwin Hubble made the groundbreaking discovery that distant galaxies are receding from us, implying that the universe is expanding in observation that led to the formulation of the Big Bang Theory. Suddenly, the universe was no longer eternal and static, but had a beginning, a history, and possibly an end. With the advent of radio astronomy, X-ray telescopes, and eventually space-based observatories like the Hubble Space Telescope, our view of the universe expanded exponentially. We detected the cosmic microwave background radiation, the faint afterglow of the Big Bang, offering strong empirical support for the expanding universe model. We mapped the distribution of galaxies across billions of light years, revealing a vast cosmic web of filaments and voids, and observed the accelerating expansion of the universe, attributed to a mysterious force now called dark energy. Alongside these advances came the exploration of our own solar system, beginning with robotic probes like the Soviet Luna missions and the American Mariner and Voyager programs. Humans landed on the Moon in 1969, a milestone in space exploration that forever altered our perspective of Earth as a fragile blue marble adrift in the void. Mars rovers, comet landers, and deep space telescopes have continued this quest, each mission peeling back another layer of cosmic ignorance. As our tools grew more sophisticated, so did our theories. Quantum mechanics and relativity, once separate realms, began to merge in the search for a unified theory of everything, giving rise to speculative models such as string theory, loop quantum gravity, and the multiverse hypothesis. While still unproven, these theories attempt to reconcile the behavior of the very small with the structure of the very large, pointing to deeper truths yet to be uncovered. Throughout this journey, one of the most important conceptual developments has been the idea of the observable universe, the region of the cosmos from which light has had time to reach us since the beginning of cosmic expansion. This boundary, currently about 46.5 billion light-years in every direction, defines the limits of our empirical knowledge. Beyond it may lie an infinite expanse of galaxies, structures, and phenomena forever hidden from us, not because of technological limitations, but because of the fundamental speed limit of light and the expansion of space itself. This observable horizon reminds us that our understanding of the universe is inherently incomplete, framed not only by the capabilities of our instruments, but also by the nature of space-time. From the mythic skies of ancient Mesopotamia to the multi-wavelength observatories orbiting Earth today, the evolution of our cosmic understanding has been a story of ever-widening perspective, driven by curiosity, skepticism, and the relentless pursuit of truth. Each discovery has reshaped our place in the cosmos, from the center of everything to a mere speck on a minor planet in an ordinary galaxy among trillions. Yet this humbling realization only deepens the mystery and amplifies the wonder. As we continue to push the boundaries of observation and theory, we are not just uncovering the architecture of the universe, we are tracing the path of human thought itself, a reflection of our deepest desires to understand where we come from, what we are, and what lies beyond the final horizon. There is something profoundly human about looking up at the stars and wondering what's out there. It is a gesture that transcends time, culture, and geography, a silent, universal act of curiosity that has burned in the hearts of shepherds, sailors, scientists, and children alike. And yet, in our modern world of distractions, routines, and artificial lights, many of us have forgotten what it feels like to truly confront the night sky, to look into the void above and understand, even for a fleeting moment, that we are staring into a mystery so vast, so ancient, and so indifferent to our existence that it can simultaneously inspire awe and stir a quiet terror. That emotional paradox, the beauty and the fear of the unknown, is exactly why this subject matters. It speaks to something primal, something deep within us that craves understanding not just of the universe, but of ourselves. Why are we here? What does it all mean? Are we alone? These are not scientific questions alone. They are emotional and existential ones, capable of reaching into the core of who we are. To study the universe is to confront our own fragility and our own significance in ways that few other endeavors can achieve. We are made of atoms forged in the cores of Starsoar. Blood contains iron that was once part of a supernova. Our bones hold calcium born in the heart of a dying sun. This isn't poetic metaphor. It's literal truth. The cosmos is not a distant realm we merely observe. It is the very thing we are made of. That connection, once understood, is transformative. It dissolves the illusion of separation between self and sky and replaces it with a sense of belonging to a vast, ongoing story that began long before we arrived and will continue long after we are gone. But that sense of belonging comes with a shadow. When you realize just how enormous the universe is and how tiny and temporary our place in it seems, it can trigger a kind of existential vertigo. We are spinning on a rock around a star that is one of billions in a galaxy, that is one of trillions in a universe, that may be only one of many. Our lifespans, our dramas, our monuments, all of them vanish in the scale of cosmic time. The entire recorded history of humanity fits within a single blink of the universe's age. The stars we see at night are often already dead, their light just now arriving after traveling for thousands or millions of years. Time itself behaves differently in the presence of gravity and velocity. Causality, reality, and even the flow of time become fragile ideas when stretched across the cosmic landscape. And so, the deeper we look into space, the more we're forced to question the nature of reality itself and whether the things we take for granted, like time, space, matter, and consciousness, are as stable as they seem. This uncertainty can be unsettling. It can leave us feeling small, insignificant, or lost. But it can also liberate us. It can free us from the ego-driven narratives of supremacy and permanence and connect us to something greater than ourselves. The fear of insignificance is, paradoxically, the very door to a more profound meaning. It challenges us to create purpose in a universe that offers none by default, to craft stories, relationships, and discoveries that make our brief lives beautiful and meaningful against the backdrop of eternity. This is why the exploration of the universe is not just a task for scientists and engineers. It is for everyone. It is a human endeavor that invites each of us to confront the ultimate questions. What is the nature of existence? Is there order in the chaos? Or is meaning something we must bring to the universe ourselves? When we send telescopes into orbit, when we land rovers on distant worlds, when we smash particles together at near light speed, we are not just gathering data or expressing our deepest longings. We are reaching out, not just across space, but across the boundaries of ignorance and fear. Every image of a distant galaxy, every map of cosmic radiation, every measurement of dark matter is an act of defiance against the darkness. We are a species that refuses to settle for ignorance, that demands to know, even when the answers shake the foundations of our beliefs. That courage to face the vast unknown, to ask impossible questions, to pursue truth over comfort is the essence of what it means to be human. There is also a quiet intimacy in this cosmic journey, The wonder of the universe is not always about blazing galaxies or exploding stars. Sometimes it's in the silent perfection of orbital mechanics, in the fragile dance of a moon around its planet, or in the way the universe gave rise to consciousness that can ask about its own origins. When you look at the stars, you are also looking inward. You are engaging with the parts of yourself that long to understand, to connect, to endure. The same universe that stretches across billions of light years also exists in the neurons firing in your brain, in the love you feel, in the questions you whisper to yourself late at night. We often imagine space as cold and indifferent, and in a sense, it is. But within that coldness, we find warmth not from the stars themselves, but from the fire of curiosity, creativity, and courage that burns within us. To care about the universe is to care about what it means to be alive, to be conscious, to be aware of time passing and possibilities unfolding. And then there's hope. Despite the chaos, despite the fear, there is always hope in exploration. Hope that we will find others out there, that we are not alone in this vast sea. Hope that we will unlock the secrets of the universe, not just to know, but to thrive. Hope that our species, though young and fragile, might endure long enough to leave a meaningful mark on the cosmos. This hope is not naive. It is resilient. It is built into our DNA, encoded in our myths, echoed in our art, and etched into the very languages we use to describe the stars. Every spacecraft launched, every experiment conducted, every question asked is a declaration that we still believe in something greater. Not in gods or fate, but in possibility, in the unyielding belief that there is more to learn, more to see, more to be. So yes, people should care about the universe, not just because it is scientifically important, but because it is personally meaningful. It is the canvas of our greatest hopes and fears, the mirror of our minds and the cradle of our atoms. It makes us feel small, so that we may grow big in spirit. It challenges our ignorance, so that we may become wise. It threatens our illusions, so that we may find truth. In the face of the vast unknown, we find a reason to become more fully human by shrinking from the darkness, but by reaching into it with open eyes and open hearts. This emotional engagement is not a luxury. It is the engine of all discovery. And as long as we continue to feel wonder, fear, and longing when we look into the stars, the universe will remain not just a physical space, but a sacred Onia realm of infinite mystery that reflects the boundless depth of our own inner worlds. Have you ever truly considered what it means to exist in a universe that you can't fully comprehend? Not in an abstract or philosophical sense, but in the raw, immediate reality of your life, your thoughts, and your place in the cosmos? Every day, we operate within a narrow slice of understanding, waking up, moving through routines, interacting with others, rarely pausing to consider that we are moving on a rock, spinning around a star in a galaxy, drifting through a constantly expanding universe, part of a structure so vast and intricate that our minds can barely begin to hold it. What if we've barely scratched the surface of what reality even is? What if time isn't linear? What if space isn't empty? What if there are dimensions wrapped around us right now, invisible yet fundamental, shaping everything we think is solid, predictable, and real? These aren't the questions of fantasy or fiction, they are at the heart of modern physics and cosmology. And they're not just for scientists in white coats. These questions belong to all of us, because they define the very stage on which our lives play out. What if what we call the laws of physics are just local rules, temporary and specific to this corner of the cosmos? What would that mean for our understanding of truth or identity? If consciousness is somehow connected to quantum processes, some theories suggest, what does that say about free will, about the soul, about the limits of what the human mind can know? And perhaps most importantly, are we alone? If we are the only intelligent life in the observable universe, then the burden of meaning rests entirely on our shoulders. But if we're not, if intelligent beings exist elsewhere, developing their own stories under alien stars, what happens to our concept of uniqueness? These are not just speculative questions. They are invitations open doors into deeper thought, into conversations that extend beyond textbooks and into cafes, dinner tables, classrooms, and late-night walks under the stars. Why does this matter to you personally? Because these cosmic mysteries aren't out there, they are in here, inside your very perception of reality. You trust your senses, but they're limited. You trust your intuition, but it evolved to help your ancestors survive on the savannas of Earth, not to grasp the curvature of space-time or the fabric of the quantum field. You live inside a body made of stardust, operating on a planet whose core was forged in ancient collisions, in a universe that could collapse or expand forever. And yet you rarely stop to marvel at that. Isn't it strange that the closer science gets to describing how the universe works, the more it sounds like poetry, like art, like something spiritual in the deepest sense? There's a reason for that. We are emotional creatures living in a rational universe, trying to make sense of mysteries that might not have tidy answers. But the journey, the act of asking, is what binds us, generation after generation. When we look to the stars and ask, why? We're not just looking outward. We're seeking the hidden architecture of truth, of reality, of self. And now we're standing on the edge of a new era, one where our questions might soon meet answers. With the James Webb Space Telescope peering deeper into time than ever before, with particle colliders smashing matter into subatomic truths, with AI accelerating data analysis and pattern recognition, we are closer than ever to shattering the barriers between the known and the unknown. What will we find? A unified theory that explains everything? Proof of the multiverse? A message from another civilization? Or perhaps something no one has imagined, a new paradigm that reframes not just the universe, but consciousness itself? Imagine waking up one day to news that changes everything. A mathematical proof of higher dimensions, an image of life on an exoplanet, a successful test of quantum gravity, or the detection of a signal from beyond our galaxy. These are not distant fantasies. They are genuine possibilities, and they would alter how we see ourselves, how we govern, how we love, how we fear, how we dream. What would happen to religion, to politics, to education, to the stories we tell children about who they are and where they come from? How would knowing that we are part of a multiverse, or that time travel might be physically possible, or that we are not the only conscious beings in the universe, reshape our ethics and responsibilities? Would we become more unified as a species or fracture further under the weight of change? The answers aren't obvious, and that's exactly why we must engage. These aren't just scientific outcomes. They are cultural, emotional, and psychological tremors waiting to unfold. And your voice matters in that process. Your imagination, your curiosity, your fears, and your insights all have a place in this unfolding story. So ask yourself, what do you believe about reality? Where do you think the universe ends, if it ends at all? Do you believe in fate or randomness? In design or accident? Do you think science can eventually explain everything? Or will there always be a mystery just beyond the edge of our knowledge? These questions don't require degrees in astrophysics. They require only attention, wonder, and a willingness to think beyond the surface. Start a conversation with a friend, a teacher, a stranger. Share your ideas, debate them, be wrong. Learn something new. Watch the stars together and talk not just about what you see, but about what might be out there. Read the stories of ancient cultures and how they interpreted the skies. Read the latest theories and how they disrupt our expectations. Connect the dots between the past and the present, the myth and the measurement, the dream and the data. This mystery belongs to everyone and not just those in labs or observatories. It belongs to the dreamers, the skeptics, the artists, the believers, the wanderers. In a time where division, distraction, and noise threaten to drown out deeper reflection, the cosmos offers something rare. A shared question too big for any single ego. A silence so vast it humbles us into listening. And in that silence, there's room for dialogue, for rediscovery, for transformation. The universe is speaking not in words, but in radiation, gravity, motion, and time. And it's asking us not just to observe, but to participate. You are part of the story of the cosmos. Your atoms, your questions, your choices, they all matter. What will you do with that knowledge? Will you look away, comforted by the familiarity of the known? Or will you lean into the unknown, allowing it to shape your thoughts, your values, your future? The next chapter of discovery is unwritten. It might be penned in equations, or etched in binary, broadcast across stars, or buried in ice on a distant moon. But it will also be written in your words, your dreams, your voice in the chorus of curiosity. Don't wait for answers to be handed to you. Go ask, go seek, go wonder out loud. Because the universe isn't just out there waiting to be discovered. It's already inside you, waiting to be awakened. Far beyond the noise of cities and the pulse of our daily lives lies a setting so vast, so still, and so alien that it resists the limits of our imagination. Space is not empty, it is a living canvas of unimaginable scale, stitched together with light, dust, fire, and time. The deeper we peer into the cosmos, the more we are immersed in a world that operates by rules so foreign they may as well be magic. Picture yourself drifting in the intergalactic medium, far from any star or planet, suspended in absolute silence. Around you, galaxies hover like lanterns in an ocean of ink spirals, with arms flung wide in graceful arcs, glowing cores of incandescent fury, halos of ancient stars, whispering stories from billions of years ago. Some of these galaxies collide, their shapes twisting into one another in slow, gravitational ballets that take hundreds of millions of years to unfold, birthing new stars in luminous bursts as gas and dust are compressed under tremendous forces. Others are dead, long past the age of star formation, their lights dim, their structures crumbling into the cosmic dark. Yet even between these island universes, space is far from empty. Invisible scaffolding spans the cosmos, made of something we cannot see but know must exist: dark matter, the silent architect of galaxies. It does not emit or absorb light. It does not interact with ordinary matter in any direct way. And yet, its presence can be inferred by the way it bends space and distorts light, revealing itself through gravitational lensing, like an invisible hand warping the fabric of the universe. It weaves the cosmic web, a sprawling network of filaments and nodes, where galaxies cluster at intersections, separated by yawning voids that stretch for millions of light years, nearly devoid of anything at all. These voids are the quietest places in existence, pockets of profound stillness where time seems to flow without resistance, and the distances between particles are so vast that even a single atom becomes a rarity. Above and below the scale of galaxies lies another kind of wonder: the stars themselves, born in clouds of molecular gas, collapsing under gravity until nuclear fusion ignites at their cores. Some live short, brilliant lives, ending in spectacular explosion supernovae that send heavy elements scattering into the cosmos, seeding the next generation of stars and planets. Others end as white dwarfs, neutron stars, or black holes remnants, so dense and exotic that they warp time and space in ways we still struggle to fully grasp. Black holes, in particular, are nature's most extreme laboratories. Their gravity is so intense that nothing, not even light, can escape once it crosses the event horizon. Yet recent discoveries have shown they aren't entirely silent. Some black holes emit powerful jets of radiation and matter, reaching across entire galaxies, shaping their environments in ways we are only beginning to understand. Some may even contain answers to the most profound questions in physics about entropy, quantum information, and the nature of space itself. Then there are the phenomena that defy all expectations. Quasars, which are so bright they outshine entire galaxies. Pulsars, spinning neutron stars that flash beams of radiation like cosmic lighthouses. And gamma-ray bursts, the most energetic events since the Big Bang. Speaking of which, the Big Bang itself is not just a theory about the origin of the universe, it is a description of its unfolding, the expansion of space and time from an unimaginably hot and dense beginning. The echo of that moment still hums in the background of the universe as cosmic microwave background radiation, a near-perfect thermal imprint of the early cosmos that scientists have mapped with exquisite precision. It reveals subtle fluctuations, tiny variations in temperature and density that would eventually become galaxies, stars, and planets. This ancient light, reaching us from a time when atoms had only just begun to form, is a message from the edge of time, a cosmic fossil preserving the story of everything. Amidst these phenomena, key figures have emerged, scientists whose curiosity and brilliance have changed the way we see the universe. Albert Einstein, whose general theory of relativity redefined gravity not as a force, but as the warping of space-time itself. His equations unlocked the possibility of black holes and the expansion of the universe. Edwin Hubble, who provided the observational proof that the universe is expanding, leading to the birth of modern cosmology. Vera Rubin, whose work on galaxy rotation curves provided the first compelling evidence for the existence of dark matter. Stephen Hawking, whose insights into black hole thermodynamics and quantum gravity brought us closer to a unified theory of physics. More recently, scientists like Brian Greene, Lisa Randall, Kip Thorne, and Neil deGrasse Tyson have become public voices for the cosmos, translating complex ideas into stories that ignite imagination. Behind them are teams of researchers, data analysts, engineers, and dreamers who build the machines and write the code that turn curiosity into discovery. The tone of this exploration is a careful balance of awe, humility, and relentless inquiry. Awe, because the universe is staggeringly beautiful and complex. Humility, because even our best theories remain provisional, incomplete, and limited by our perception. And relentless inquiry, because each answer leads to deeper questions. Why is the universe fine-tuned for life? Is it coincidence, necessity, or something else entirely? What is dark energy, the mysterious force accelerating the universe's expansion? Is it a property of space itself, a new kind of field, or the echo of other universes brushing against our own? Are the laws of physics fixed, or do they evolve over time? These questions set the atmosphere of modern cosmology not as a temple of certainty, but as an unfolding narrative, rich with unknowns, where each new observation could rewrite the rules. As you step into setting this great cosmic stage, it's impossible not to feel a sense of smallness. But that smallness is not despair. It is the kind of smallness that inspires. The kind that says, you are part of something unimaginably vast, and your ability to ask questions, to imagine, to explore, is itself a product of that vastness. You are the universe, thinking about itself. Every heartbeat, every thought, every discovery is an expression of stardust becoming aware. When we listen to the signals from distant galaxies, we are not eavesdropping on strangers. We are listening to our own origins. When we chart the motion of stars, we are mapping the echoes of ancient collisions that shaped everything we see and are. This is not fiction. This is not metaphor. This is reality, as best as we can currently understand it. And there is so much more to understand. The atmosphere of the cosmos is not one of silence, but of hidden symphonies. Not one of darkness, but of light still traveling, still reaching us across gulfs of space and time. It is not distant from you, it is within us. Every cosmic mystery, every anomaly, every elegant equation or unexpected signal is an invitation. An invitation to think deeper, feel wider, and wonder endlessly. As long as we are willing to listen, to look, to ask, and to risk being wrong, the universe will continue to reveal its secrets. And with each revelation, we step closer to understanding the greatest story ever told, the story of everything. As we venture ever deeper into the mysteries of the cosmos, guided by the faint glow of distant galaxies and the sharp precision of our instruments, a haunting question begins to emerge. What if there is no final answer? What if the edge we seek, the fundamental truth of the universe, is not a destination waiting to be discovered, but a mirage that recedes the closer we get? This is not pessimism, but the unsettling possibility that the universe itself may be fundamentally unknowable in certain ways, that its ultimate secrets may remain forever beyond the reach of human comprehension. Even as we celebrate the immense strides of science and technology, there are quiet, persistent signs that suggest we may be approaching a boundary not of distance, but of understanding. Paradoxes are whispering from the corners of our theories, inconsistencies that seem small at first but may, in time, unravel entire frameworks of thought. They foreshadow a cosmic conflict, not between civilizations or galaxies, but between reality and our ability to grasp it. One of the most glaring of these paradoxes lies in the heart of physics itself, the incompatibility between quantum mechanics and general relativity. On their own, these two pillars of modern science have proven remarkably accurate. Quantum mechanics governs the behavior of particles at the smallest scales, revealing a probabilistic, uncertain, and interconnected reality where observation itself alters outcome. General relativity, by contrast, describes gravity and the fabric of space-time on the largest scales, from planetary orbits to the warping effects of black holes. Yet when these two theories are applied to the same situation, such as the singularity at the center of a black hole, or the moment of the Big Bang, they break down. Equations yield infinities. Predictability vanishes. Reality, as we know it, collapses into contradiction. Despite decades of effort, a complete theory of quantum gravity remains elusive. String theory, loop quantum gravity, and other attempts offer mathematical elegance, but they remain speculative, unproven, and often untestable with current technology. This theoretical dissonance is not just a problem of calculation, it is a sign that we are missing something fundamental. Observational limitations add another layer to this growing uncertainty. Consider the cosmic horizon, the boundary of the observable universe. Due to the finite speed of light and the age of the universe, there's a limit to how far we can see. Anything beyond that limit is forever out of reach, not because it doesn't exist, but because its light has not had time to reach us. And due to the accelerating expansion of space, it may never will. We can only build our cosmological models on what we can observe, yet we know there is more, perhaps infinitely more beyond that edge. The visible universe may be a drop in an endless ocean, and if the properties of the universe vary beyond our observational horizon, the laws of physics themselves differ in other regions, then our understanding is inherently provincial. We may be drawing grand conclusions from a tiny and unrepresentative sample of reality. We may be living in a cosmic anomaly without even knowing it. Even within our visible universe, there are signs of strangeness that hint at deeper layers of complexity. The behavior of dark energy, the repulsive force driving the accelerated expansion of the universe, remains a mystery. Is it a property of space itself? Is it constant or evolving? Why does it have the value it does, a value that seems improbably small, yet precisely tuned to allow for galaxies, stars, and life? If dark energy were just slightly different, the universe would have torn itself apart or collapsed long ago. This fine-tuning problem, along with similar puzzles surrounding fundamental constants, has led some physicists to propose the multiverse theory. The idea that our universe is just one of many, each with its own physical laws. But here lies another dilemma. These other universes are causally disconnected from ours. How could we ever confirm their existence? Are we building explanations we can never test? Are we crossing the line from science into metaphysics? Or simply expanding our definition of what science can be? The rise of the information paradox in black hole physics further deepens the tension. According to general relativity, anything that falls into a black hole is lost forever. But quantum mechanics insists that information cannot be destroyed. So which is it? Hawking's original calculations suggested information is lost, violating quantum rules, but newer theories propose it might be encoded in the event horizon or escape as Hawking radiation. Yet no one has resolved the paradox definitively, and experiments to test these ideas remain far beyond our current capabilities. These thought experiments don't just challenge our math, challenge our deepest assumptions about reality, time, and causality. Even the fabric of time itself may be an illusion. Some physicists argue that time does not flow, that it is an emergent property of entanglement, or a perceptual construct arising from entropy. If true, then our entire experience of life, sequence, memory, and motion is based on something that doesn't exist in the way we think it does. And if time is not fundamental, what does that mean for cause and effect, for identity, for the possibility of free will? These are not fringe ideas. They are serious proposals by respected physicists grappling with the implications of our most advanced models. And as these ideas proliferate, so too does the sense that we are not approaching a final answer, but a crossroads where our traditional modes of understanding may no longer suffice. Technology, too, is both a savior and a limitation. Our instruments are now so precise that they generate data faster than we can interpret it, revealing anomalies in cosmic background radiation, in particle behavior, in galactic rotational, of which demand explanations we are not yet equipped to give. At the same time, we face the challenge of building larger, more complex machines to test our theories. Colliders that require national budgets, telescopes launched beyond Earth's orbit, detectors buried in mountains or deep under the sea. As costs rise and returns diminish, we must ask whether there is a ceiling to empirical inquiry, a point at which the questions outpace our ability to investigate them. Or worse, What if the answers are hidden behind cosmic censorship, a principle suggesting that nature prevents us from observing the most extreme regions of space-time, such as the singularities at the cores of black holes? Are we being shielded from the truth by the very structure of the universe? And yet, for all these challenges and contradictions, the pursuit continues. We build models that work in limited domains, knowing they are incomplete. We test hypotheses with simulations, knowing they may never be observed. We stare into the abyss, knowing it may not respond. But that tension between what we know and what we can never know is not a failure of science. It is its fuel. Every paradox is a beacon. Every limit is a provocation. The edge may never be found not because it doesn't exist, but because it is always one step beyond the reach of our current tools, our current minds, our current myths. Just as the horizon recedes as you approach it, so too may ultimate truth remain forever out of grasp, not mocking us, but inviting us to grow. This is the true conflict at the heart of cosmology. Not a war of ideas, but a dance between light and shadow, certainty and doubt, knowledge and mystery. In this dance, we are the fragile yet determined partners. We are creatures of stardust and entropy, of logic and longing. Our tools are limited, our time is short, but our questions are infinite, and our courage to ask them remains undiminished. Even if we never find the final edge, even if reality proves too vast or strange to fully decode, the very act of seeking transforms us. It sharpens our intellect, deepens our empathy, humbles our arrogance, and elevates our imagination. The universe may not owe us answers, but we owe it our questions. And so, we look out again into the dark, into the silence, into the paradox and ask not, will we reach the edge? But, who will we become in trying? At the heart of modern cosmology lies a conflict that has grown more intricate and urgent with every breakthrough in intellectual and existential struggle between competing visions of the universe, each backed by elegant mathematics, compelling logic, and incomplete evidence. As our understanding of the cosmos deepens, so too does the friction between the foundational frameworks we use to describe it. This conflict is not merely academic. It is the crucible in which the future of science, and possibly our conception of reality itself, will be forged. Nowhere is this tension more palpable than in the question of the universe's edge, whether it exists at all, and if it does, what it looks like, how it behaves, and what lies beyond it. Cosmologists, philosophers, and physicists find themselves entangled in an ever-growing web of contradictions, forced to choose between models that are internally consistent but externally incompatible. It is a war of paradigms, of finite versus infinite, of simplicity versus complexity, of what we can observe versus what we can only infer. At the core of this battle is the foundational divide between general relativity and quantum mechanics. General relativity, Einstein's magnum opus, describes gravity as the curvature of space-time caused by mass and energy. It accounts for the behavior of galaxies, black holes, and the expansion of the universe with astonishing precision. But it breaks down at quantum scale-sat singularities, like those inside black holes, or at the origin point of the Big Bang where space and time themselves collapse into mathematical absurdities. Quantum mechanics, on the other hand, governs the subatomic world with unmatched accuracy, predicting the behavior of particles, fields, and forces in ways that have been experimentally verified countless times. Yet, it cannot explain the gravitational force in a consistent way. The two theories, our most successful scientific achievements, refuse to speak the same language. This schism is more than a technical problem. It is a philosophical wound in the body of science, a reminder that even our best tools may be insufficient to describe the full architecture of the cosmos. The conflict escalates when we try to map these theories onto the universe as a whole. Is the universe infinite, stretching endlessly in all directions, never repeating, never ending? Or is it finite but unbounded, like the surface of a sphere, looping back on itself in higher dimensional space? Each option carries its own implications and problems. An infinite universe raises paradoxes of measure and probability. How do you define a meaningful fraction of infinity? How do you make statistical predictions in a space where all outcomes occur an infinite number of times? A finite universe, by contrast, demands an edge of some kind, spatial or temporal, which then must be explained. What lies beyond the boundary? Is there a boundary at all? Or are we trapped in a bubble, one universe among many, each with its own physical laws? These competing views feed into the debate between inflationary cosmology and alternative theories. Inflation, the idea that the early universe underwent a brief exponential expansion, solves several key problems, such as the horizon problem, the flatness problem, and the uniformity of the cosmic microwave background. It has strong observational support. Yet inflation also leads naturally to the idea of eternal inflation, a process in which different regions of space inflate at different rates, producing an infinite multiverse of causally disconnected pocket universes. Each of these could have different values for fundamental constants, different laws of physics, even different numbers of dimensions. This multiverse model explains fine-tuning without invoking design, but it comes at the cost of testability. If these other universes cannot be observed, are we still doing science or drifting into metaphysical speculation? This tension is further strained by string theory, one of the leading candidates for a theory of everything. String theory posits that all particles are vibrating strings existing in a 10 or 11-dimensional space, many of whose dimensions are compactified, curled up at scales far smaller than we can detect. The theory offers mathematical beauty and potential unification, but it also allows for an almost infinite landscape of possible universes, each corresponding to different configurations of those extra dimensions. Again, we face a loss of predictability. If everything is possible, how do we explain why we observe what we do? Where is the edge that distinguishes reality from possibility? Cosmologists are not blind to these issues. They wrestle with them daily, torn between their commitment to empirical evidence and the need to explore theoretical frontiers. Some cling to the observable universe as the only valid object of study, insisting that anything beyond it, no matter how plausible, must be excluded from serious discussion until it yields measurable predictions. Others argue that the edge of scientific discovery now lies precisely in the unobservable, that to ignore these questions is to stagnate. In the background of this debate is a deeper question. What is science for? Is it a tool for explaining what we can see and test? Or is it a method for extrapolating deeper truths from the patterns we find? Even observational evidence itself does not always clarify the conflict. The cosmic microwave background, the afterglow of the Big Bang, is remarkably uniform, but it also contains tiny anomalies that could hint at new physics. The distribution of galaxies on large scales suggests a structure too vast to be explained by random fluctuations alone, hinting at pre-inflationary forces. Gravitational wave detections are revealing black hole mergers that defy existing models of star formation. The Hubble tension discrepancies between different measurements of the universe's expansion rate remains unresolved, suggesting either unknown systematic errors or new physics entirely. Each new piece of data simultaneously confirms and complicates our models, pushing cosmologists toward more elaborate theories, and yet none of these theories is yet complete. The map of reality grows more detailed, but the territory it represents remains elusive. Meanwhile, the very concept of the edge becomes harder to define. Is it a spatial boundary, a temporal one, or a limit of understanding? Some suggest the universe is a hologram, that all the information within a volume of space can be encoded on its surface, reducing the question of edges to one of information storage. Others propose that space-time itself is emergent, the product of quantum entanglement, in which case the edge may be not a place, but a phase transition. In both cases, the conflict intensifies. Not only do our traditional categories fail us, but the universe itself may be structured in ways that defy intuition altogether. How do we map a reality that does not behave like space or time as we know them? This struggle to define the cosmos is not new. From the geocentric to the heliocentric model, from Newton's clockwork universe to Einstein's relativistic spacetime, every era has had to abandon cherished assumptions to embrace new truths. But today's conflicts are of a different order, not merely shifts in perspective, but crises of coherence. We are not replacing one theory with another. We are confronting the possibility that no single theory can ever explain it all. That truth may be fragmented, contingent, or forever inaccessible. And yet, in that very struggle lies the spirit of cosmology. It is not a failure to admit conflict, it is a triumph of inquiry to face it head-on. Cosmologists stand at the frontier, equipped with equations that near but not quite describe the universe, and data that nearly but not quite confirm them. They are explorers charting a sea whose shape changes as they sail, whose storms are paradoxes, and whose horizon is always just beyond reach. They argue, they doubt, they calculate, and they dream. Some hope for a grand unification of final theory that resolves all contradictions. Others suspect such unity may be impossible, that the universe is irreducibly complex, its truths always contextual. But all agree on one thing: the conflict is not a barrier. It is the engine of discovery. As we follow this struggle, we are not merely spectators, we are part of it. Our questions, our perspectives, our willingness to engage with uncertainty all shape the search. The edge we seek is not only out there in the stars, it is also in us, in our minds, our models, and our courage to imagine what might lie beyond the known. Whether the universe is finite or infinite, singular or multiversal, static or dynamic, we must confront the reality that no theory, no telescope, and no simulation can ever be final. The cosmos resists closure because it is alive with possibility. And in that resistancing, that beautiful, relentless conflict, we find not defeat, but the essence of science itself. The willingness to ask questions whose answers we may never fully grasp, but whose pursuit defines who we are. If the universe has no edge, no boundary where it stops, turns back, or gives way to something else, then our understanding of reality must shift in ways that affect not only physics and cosmology, but also philosophy, identity, and meaning itself. This idea, at first, seems abstract, but linger with it long enough, and it becomes a deeply personal realization. A universe without an edge does not just mean an endless expanse of space. It suggests that our frameworks for measuring, comparing, or even defining reality might be fundamentally incomplete. For physicists, the absence of an edge removes the possibility of a neat, closed systema final frame of reference from which we can examine all that is. It denies the notion of a total picture. It implies that there will always be more to see, more to know, more that lies forever out of reach. For cosmology, this isn't merely a boundary issue, it is a signal that our models, elegant as they may be, are approximations layered over a reality too complex or too infinite to be contained in human terms. In a universe with no edge, the fundamental equations of physics lose some of their anchoring power. Models that assume boundary conditions, like the shape of spacetime, the topology of the cosmos, or the behavior of energy at infinity, must be rewritten or reinterpreted. For example, many cosmological simulations rely on a finite grid, a defined space in which energy and matter can be calculated, conserved, and understood. If space itself has no limit, those assumptions may not hold. Conservation laws, thermodynamics, and the evolution of entropy, all of which depend on system boundaries, may need reformulation. If there's no total volume, how do we quantify the distribution of energy across the universe? If there's no outside, what does it mean to speak of expansion? The concept of edge is often implicit in our physics. Remove it, and a cascade of consequences follows. Models of the early universe, of cosmic inflation, of gravitational wave propagation each would need adjustment or even reinvention. But more than that, a universe with no edge stretches our philosophical grasp of existence. It means that there is no outside to retreat to, no conceptual high ground from which to observe the cosmos in its entirety. We are not merely small in a vast system, we are embedded, infinitely so, within a structure that may have no frame at all. That realization forces us to abandon the comfortable idea that the universe is a thing we can one day fully know, measure, or comprehend. Instead, it may be a process in unfolding, a become forever outpacing our best tools and deepest thoughts. The pursuit of knowledge, then, is not a race to a finish line, but a lifelong pilgrimage into mystery, a journey without arrival. For those drawn to certainty, this can be unsettling. But for those open to wonder, it is exhilarating. It means that meaning is not located in answers, but in the questions themselves and the fact that we can even ask them at all. the existential impact is profound. If the universe has no edge, then where are we? Not in the center, certainly. Not near the end. We are somewhere in an unbounded ocean of space and time, on a planet that orbits an ordinary star in an ordinary galaxy, with no special vantage point or cosmic privilege. And yet, somehow, we are conscious of this fact. We can look out into the void and not only see galaxies, but feel something about them: curiosity, fear, longing. In a universe with no edge, our existence takes on a different kind of meaning. Not one granted from outside, but one generated from within. We are not here for a reason dictated by the cosmos. We are the ones who create reasons. In that way, we become co-authors of reality, even if we cannot control its laws. The lack of an edge means we are not contained, and thus not defined, by limits. We are part of an unfinished story, one that is not leading to a final answer, but expanding with every question we ask. The consequences ripple into metaphysics. Without an edge, the question, what came before the universe, becomes incoherent, or at least irrelevant. There is no outside, no before, no separate realm into which we can step to find origins or conclusions. Space and time themselves may be emergent property solutions, born from deeper, more abstract principles. Some theories suggest that space-time arises from quantum entanglement, or from informational structures we cannot yet visualize. In these views, the universe is not a physical place so much as a web of relationships, and our physical intuition sedges, distances, beginnings, endings are artifacts of perception. If true, then our most basic experiences of reality are shadows of something deeper, and to explore the cosmos is to slowly uncover the geometry of the hidden. Practically, the absence of an edge poses a challenge for measurement. Our current telescopes have a limit, defined by the age of the universe and the speed of light, about 46.5 billion light-years in every direction. This is the observable universe. But if space extends beyond this, perhaps infinitely, then everything we know is a local sample. It's like trying to understand an ocean from a teaspoon. Statistical assumptions that underpin our cosmological models, such as isotropy and homogeneity, rest on the Copernican principle that we do not occupy a special place in the universe. But if we are in a localized bubble, an unusual patch of a larger structure, that assumption may be flawed. Our measurements may not generalize. Our theories may describe this corner of the cosmos well, but fail utterly elsewhere. These limitations demand new physics, new ideas that go beyond the frameworks we've inherited. Just as Newtonian mechanics gave way to relativity and quantum theory, we may now be on the cusp of another transformation. We need theories that can unify the probabilistic chaos of the quantum world with the smooth, geometric elegance of general relativity. We need models that can describe space without boundaries, systems without closure, infinities without paradox. And we need tools, mathematical, computational, conceptual, that can help us think in ways we currently cannot. These may come from quantum gravity research, from string theory, from loop quantum cosmology, or from entirely unexpected places. They may involve abandoning cherished assumptions, like locality, determinism, or even objectivity. But whatever form they take, they must help us live with the truth that is becoming harder to deny, that the universe is more than just big. It is fundamentally open, fundamentally strange, and fundamentally beyond the full grasp of any single perspective. Yet within this immensity, there is hope. A universe with no edge is a universe without walls. No final frontier, no ultimate barrier, no end to discovery. It is a place where every answer births more questions, where understanding is a living process, not a fixed goal. In such a cosmos, there is always room for growth, for deeper insight, for broader compassion, for higher creativity. We are not racing toward a finish line. We are unfolding, becoming, participating in the evolution of awareness itself. And that awareness, the capacity to ask, to wonder, to feel, is itself a miracle, forged in the crucible of stars, shaped by billions of years of cosmic history, and now, looking back at its origins through the lens of consciousness. So what if the universe has no edge? Then we must abandon the illusion of arrival. we must embrace the infinite not just as a mathematical idea, but as a way of being. We must cultivate a science that is humble, adaptive, and imaginative. We must teach ourselves to think beyond boundaries, to model without walls, to love the unknown not as a threat, but as an invitation. And in doing so, we may finally understand that the greatest discovery is not a place or a particle, but a perspective, one that sees the cosmos not as something to conquer or complete, but as something to join, something to become. There are moments in the history of science when the landscape of understanding shifts so dramatically that everything before feels like a prologue. These are not simply new discoveries, they are turning points, revelations that reshape not only our knowledge of the universe, but our vision of what's possible. In cosmology, such moments are rare and monumental. They do not come softly. They arrive with data that defy expectations, with patterns that break the rules, with questions that demand new languages to be answered. The last few decades have delivered such turning points so profound that they have forever changed the trajectory of our pursuit of the ultimate cosmic truth. From the discovery of dark energy, to the precision imaging of the cosmic microwave background, to the astonishing views brought to us by modern space telescopes, each revelation has added a new twist to our cosmic narrative. And together, they signal that we may now be entering a new era of cosmology, one defined not by static models or final theories, but by dynamism, uncertainty, and expansion, both literal and intellectual. One of the most startling revelations came at the end of the 20th century, when two independent teams studying distant supernovae expected to find that the universe's expansion was slowing due to gravity. What they found instead was the opposite. The universe is not just expanding, it's accelerating. This discovery was a thunderclap. It implied that some previously unknown force, dubbed dark energy, was counteracting the pull of gravity on cosmic scales. Unlike dark matter, which has gravitational effects and clusters around galaxies, dark energy appears to act uniformly throughout space, pushing it apart. It is not merely an exotic curiosity. It dominates the energy budget of the universe, making up roughly 68% of the total content of the cosmos. And yet, we do not know what it is. Is it a property of the vacuum? A new kind of field? The footprint of a deeper layer of reality? Its discovery forced cosmologists to rewrite the standard model of the universe and introduced a new mystery that may take centuries to resolve. Dark energy's role in shaping the universe is nothing short of profound. It dictates the fate of cosmic evolution. If its influence continues to grow, it could lead to a scenario known as the Big Rip, in which galaxies, stars, planets, and even atoms are ultimately torn apart by the relentless expansion of space. Alternatively, it might stabilize, leading to a cold, dark, ever-expanding universe. The key lies in its equation of state, how its pressure relates to its energy density, something scientists are still trying to pin down through precision measurements of distant galaxies, the cosmic microwave background, and large-scale structure formation. Every new observation helps refine our understanding of how dark energy works, but it remains, for now, an invisible puppet master guiding the expansion of the cosmos. As this mystery unfolded, technology was evolving at an extraordinary pace. Telescopes that once merely gathered light from stars now measure radiation across the entire electromagnetic spectrum, from radio waves to gamma rays, revealing a universe teeming with complexity. The Hubble Space Telescope, launched in 1990, became a symbol of this revolution. It showed us galaxies as they appeared billions of years ago, provided deep field images that revealed the immensity of the cosmic web, and captured the birth and death of stars with breathtaking clarity. Hubble's success laid the groundwork for even more powerful instruments, such as the Planck satellite, which mapped the cosmic microwave background with unprecedented accuracy, and the James Webb Space Telescope, JWST, which began operations in the 2020s. JWST is perhaps the most ambitious scientific instrument ever built. It operates in the infrared spectrum, allowing it to see through cosmic dust and to observe the earliest galaxies forming just a few 100 million years after the Big Bang. Its images are not just beautiful, they are revolutionary. Early JWST observations revealed galaxies that appeared more massive, structured, and mature than expected at such early times. challenging our current models of galaxy formation and suggesting that the processes of star birth and cosmic assembly may have begun earlier or operated more efficiently than previously thought. Some of the structures JWST is capturing shouldn't exist, at least not according to our standard timelines. These surprises are not errors. They are the friction points of discovery signs that our theories may need adjustment, or that new physics may be waiting to be uncovered. Other telescopes, like the European Space Agency's Gaia Observatory, have mapped the motion of over 1 billion stars in our galaxy, creating a dynamic, three-dimensional model of the Milky Way that helps us understand its structure, formation history, and future evolution. The Event Horizon Telescope, a global array of radio dishes, gave us the first image of a black hole's event horizon, confirming predictions of general relativity with stunning clarity. Meanwhile, gravitational wave detectors like LIGO and Virgo have opened an entirely new window on the universe, detecting ripples in space-time caused by violent collisions of black holes and neutron stars. These are not just new observations, they are new senses, allowing us to hear the universe for the first time. Each detection is a data point in a growing symphony of cosmic events, revealing a dynamic, energetic universe far more active and interconnected than we once imagined. As the data flood in, cosmologists are both empowered and challenged. The sheer volume of information, made possible by high-performance computing, machine learning, and global collaboration, has transformed how science is done. Simulations of the universe, once limited by computing power, can now model the evolution of galaxies, the distribution of dark matter, and the formation of large-scale structure with stunning realism. These simulations often predict things that our telescopes then confirm, but they also reveal gaps, inconsistencies, and surprises that push theory forward. For example, simulations have helped identify discrepancies in the Hubble constant, the rate of expansion of the universe when measured using early universe, cosmic microwave background data versus late universe, supernovae, and galaxy data. This Hubble tension suggests that either unknown systematics are affecting our measurements or that new physics is needed to explain the difference. Perhaps dark energy evolves over time, or perhaps there is an unknown particle or interaction at work. The turning point, again, lies not in the certainty of answers, but in the momentum of questions. These scientific revolutions have brought with them a new tone in cosmology that blends excitement with humility. We are no longer in the era of final theories. We are in the era of paradoxes, of bold ideas, of constant revision. The universe is not a puzzle to be solved once and for all, but a living mystery that deepens with every layer we peel back. We've discovered that the majority of the universe is made up of things we cannot see or fully understand: dark matter and dark energy. We've seen that space is not passive, but dynamic. We've learned that the universe is not only expanding, but accelerating. And we've begun to understand that time, space, and matter are not the fundamental realities we once believed them to be, but emergent properties arising from deeper, as yet unknown principles. Perhaps the most significant shift is in how we think about our place in this cosmos. With every turning point, we become both smaller and more connected. We are not at the center of the universe, but we are a part of it. Our minds, forged in stars and shaped by evolution, are capable of understanding galaxies, simulating black holes, and measuring the whisper of ancient light. We are not merely observers, we are participants in the unfolding of the universe. Each telescope we launch, each equation we write, each theory we test, is an expression of that participation, a gesture of curiosity across the gulf of space and time. The turning points of cosmology are not only about what we learn, they are about how we learn and why. They remind us that discovery is a process, not a destination. That knowledge is dynamic, provisional, and ever-expanding, and that the cosmos, in its infinite scale and mystery, is not something to conquer, but something to join. Through dark energy, through new telescopes, through the unexpected behaviors of the early universe, we are beginning to see not just more, but differently. We are learning that the universe is not just strange, it is stranger than we can imagine. But with each revelation, our imagination grows. And that, perhaps, is the most important turning point of all. What if the universe isn't what it seems? What if everything we observe, galaxies, stars, planets, even space and time themselves, are not the fundamental ingredients of reality, but emergent, encoded illusions projected from a deeper, more abstract realm? This may sound like the realm of science fiction, but it is increasingly a topic of serious consideration in the heart of theoretical physics and cosmology. As the contradictions between our best theories persist, and as new discoveries challenge long-standing assumptions, a growing number of scientists are asking whether we've been looking at the universe from the wrong angle. Perhaps it is not our observations that are flawed, but the conceptual frameworks we use to interpret them. In recent years, a suite of bold, paradigm-shifting ideas has emerged by the holographic principle, quantum information theory, and other radical perspectives that attempt to reframe the entire nature of physical existence. These new viewpoints are not just theoretical curiosities. They are changing the questions we ask, the tools we build, and the very language we use to explore the cosmos. Among these ideas, the holographic principle stands out as one of the most audacious and compelling. It proposes that all of the information contained within a volume of space, everything that happens inside it, every atom, every event, can be described by data encoded on its boundary. In other words, just as a hologram contains a three-dimensional image stored in two dimensions, the universe itself might be a kind of projection, with its true information content residing not in its interior, but on its edges. This concept originated in the study of black holes. According to the work of physicists like Jacob Bekenstein and Stephen Hawking, black holes appear to have an entropian information content that scales not with their volume, as one might expect, but with the surface area of their event horizon. This revelation led to the conclusion that, at least in the extreme case of black holes, space behaves more like a container of information than a container of matter. Later, this idea was extended in the form of the ADS-CFT correspondence, formulated by Juan Maldacena, which showed that a gravitational theory in a bulk volume of space could be exactly equivalent to a quantum field theory defined on its boundary. This is not a metaphor, it is a mathematically precise duality. It suggests that space-time itself, along with gravity, might be emergent phenomena arising from more fundamental quantum relationships. If this idea is correct, the implications are staggering. It means that our experience of space, time, and motion may be similar to the way a three-dimensional image emerges from a flat screen. The universe, in its apparent vastness, may be a kind of encoded surface, and our reality, a shadow of deeper principles. This reframes the very questions we ask in cosmology. Instead of seeking the origins of the universe in terms of initial conditions and physical forces, we may need to ask how information is encoded and processed. The early universe, the Big Bang, inflation, and dark energy may all be side effects of deeper, non-spatial mechanisms. Even gravity, the most intuitive and seemingly fundamental of forces, may be a statistical consequence of microscopic degrees of freedom, much like temperature or pressure are emergent properties of atoms in a gas. This shift in perspective leads directly into the increasingly central role of quantum mechanics in our understanding of the cosmos. Quantum theory, with its probabilistic nature, entanglement, and wave-particle duality, once seemed confined to the microscopic world. But mounting evidence suggests it may be essential for understanding cosmic-scale phenomena as well. Quantum fluctuations in the early universe, for example, are believed to have seeded the large-scale structure of galaxies we observe today. These tiny ripples in the quantum field, magnified by inflation, left imprints on the cosmic microwave background that we can still detect. In this sense, the shape of the universe, the great cosmic web of voids and filamensis, a direct consequence of quantum processes at the Planck scale. That means the structure of everything we see today has quantum roots. Furthermore, quantum entanglementa phenomenon, in which particles become linked in such a way that the state of one instantly influences the state of the other, regardless of distance, has been proposed as the glue that holds spacetime together. According to some researchers, such as Mark van Ramstonk and others working in the field of quantum gravity, spacetime geometry may emerge from the entanglement structure of an underlying quantum state. If so, then the universe is not built from particles and fields, but from information and relationships. It is not space that contains things, but the connections between things that give rise to space. This deeply relational view of reality marks a profound departure from the classical, object-based worldview. In Newtonian physics, the universe is a stage upon which matter and energy move. In relativity, the stage itself becomes dynamic, warped by gravity. But in quantum cosmology, the stage may not exist at all until it is observable, until it arises from a network of entangled states. Reality becomes not a static structure, but an ongoing process of measurement, correlation, and emergence. In such a universe, asking, "Where is the edge?" may be the wrong question. There may be no edge, no container, no outside. Instead, the universe is its own map, its own code, unfolding from within, without reference to any external point. This reframing is not just a theoretical exercise, it is changing the practice of science. New experiments in quantum information theory, condensed matter physics, and high-energy particle collisions are being designed not just to test particles, but to understand how information behaves at fundamental levels. Quantum computers, still in their infancy, offer the promise of simulating quantum systems in ways classical computers cannot. These simulations could offer insights into how space-time and gravity emerge from quantum rules, enabling us to model universes from the ground up, not with atoms and forces, but with bits and logic gates. Even the language of scientific discussion is evolving. Terms like emergence, entanglement entropy, and holographic encoding are now common in cosmology, replacing the older vocabulary of force fields and absolute space. The dialogue has shifted from "what is the universe made of?" to "how does the universe store and process information?" This shift also reopens ancient philosophical questions in a new light. If the universe is ultimately made of information, what role does consciousness play? Is observation a necessary component of physical reality, as some interpretations of quantum mechanics suggest? Are we participants in the unfolding of the cosmos, or merely passive witnesses? These are not idle speculations. They are central to the debate over the interpretation of quantum mechanics. The many worlds interpretation, the Copenhagen interpretation, and the more recent cubism, quantum Bayesianism, each offer radically different answers about the nature of reality and the role of the observer. In a holographic, information-based universe, these questions take on new urgency. They challenge us to rethink not only the external universe, but the internal one, to examine the nature of awareness, perception, and identity. Perhaps the greatest gift of this shift in perspective is not that it offers final answers, but that it expands the range of what we are willing to consider. By freeing ourselves from outdated metaphors and rigid models, we open the door to creativity, to cross-disciplinary insight, and to a deeper humility in the face of the unknown. The universe, it turns out, is not just a place, it is a question, a process, a reflection of our own capacity to imagine. We may never see the true edge of the cosmos, not because it's too far away, but because it doesn't exist in the way we think. But if we are willing to change how we look, if we're willing to entertain the idea that space is not a thing, that time is not a river, that matter is not the foundation, then we may begin to see what was hidden in plain sight all along. In the end, the cosmos may not be made of particles, strings, or even fields, but of relationships, encoded on boundaries, processed through quantum logic, and observed through the lens of consciousness. That doesn't make it any less real. In fact, it may be the most real thing we've ever considered. The shift in perspective isn't away from reality, it's toward a deeper, more connected, more nuanced version of it. And in making that shift, we move one step closer, not to solving the universe, but to becoming truly at home in it. In the grand pursuit to understand the universe, science has often rewarded us with clarity moments when confusion gives way to order, and chaos reveals a deeper harmony. But not all discoveries offer comfort. Some break the pattern, some flip the chessboard of assumptions and leave us staring at something strange, something wild, something completely outside the expected bounds of reality. These moments, these unexpected twists, are the pulse of cosmology today. Rather than bringing closure, they tear open new chapters, challenging not just our models of the cosmos, but the very frameworks of meaning, purpose, and identity. In recent decades, a series of such revelations has transformed the scientific landscape and invited us to contemplate questions that, not long ago, were the exclusive territory of philosophers, mystics, and dreamers. Are we living in just one of many universes? Could reality be simulated? Might the universe itself be an emergent illusion, constructed from principles we've only begun to imagine? These questions are no longer fringe speculation. They are at the forefront of theoretical physics and cosmology, and they may hold the key to understanding not only the nature of the cosmos, but the nature of ourselves. Perhaps the most disruptive idea of all is the multiverse, the possibility that our universe is not the whole of reality, but merely a small pocket in an unimaginably vast ensemble of universes, each with its own laws, constants, and histories. This idea did not emerge from fantasy, but from serious attempts to solve problems in inflationary cosmology, quantum mechanics, and string theory. Inflation, for example, predicts that the universe expanded exponentially in its first Momenza process, that, under certain conditions, never completely stops. This leads to eternal inflation, where some regions of space continue to inflate, forming bubble universes isolated from each other by vast expanses of inflating space. Each bubble could represent a separate universe, with different physical constants, different particles, even different numbers of dimensions. In string theory, the situation is even more extreme. The theory allows for a near-infinite landscape of possible vacuum states, each representing a different universe within the multiverse. These universes may never interact, and yet their existence could explain one of the deepest mysteries in physics. Why our universe seems so perfectly tuned for life? If there are infinite universes, then we may simply live in one of the rare ones where the laws of physics allow stars, planets, chemistry, and biology. This anthropic reasoning, though controversial, has gained traction in the absence of a more satisfying explanation for fine-tuning. But it also raises profound questions about meaning. If all possible universes exist, what makes ours special? If every possible version of you exists somewhere, with every possible choice played out in parallel, what does that say about identity, about choice, about truth? The multiverse does not just expand space, it fragments it. It replaces a singular, coherent narrative with a quantum chorus of infinite variations. And it suggests that the reality we know is not central or final, but one petal in an eternal bloom of possibility. While the multiverse stretches our understanding of space, another theory challenges our understanding of reality itself. The simulation hypothesis, popularized by thinkers like Nick Bostrom and explored through the lens of digital physics and computer science. This idea posits that our universe might be an artificial constructed simulation running on some advanced computational substrate created by an intelligence beyond our own. The argument is disarmingly simple. If it becomes possible to simulate entire universes with conscious beings inside them, and if advanced civilizations have any interest in doing so, then the number of simulated universes would vastly outnumber real ones. Statistically, it is more likely we are in one of the simulations than in the base-level reality. What began as a philosophical curiosity has evolved into a legitimate topic of scientific and technical interest. Some researchers have even proposed looking for glitches in the fabric of space, anomalies in cosmic radiation, pixelation of space-time at the Planck scale, or limits in the information content of the universe that could be interpreted as signs of computational structure. The simulation hypothesis turns our most basic assumptions upside down. It suggests that matter, energy, and space-time are not fundamental, but code. That consciousness is not the result of biology, but of processing, and that the universe has no edge, no origin in the traditional sense, because it was constructed with parameters rather than born from chaos. If true, this would not negate the beauty or meaning of the cosmos, it would redefine it. Like characters in a novel discovering they are part of a story, we would be faced with a new kind of mystery, not just what the universe is, but why it was made, and for whom. These alternative cosmologies, whether they posit multiple universes, simulated worlds, or emergent dimensions, are not meant to replace established physics, but to explore the edges where our current models fail. And those edges are everywhere. From the information paradox in black holes to the unification problem between quantum mechanics and gravity, our best theories are whispering to us that something fundamental is missing. This is not failure. It is signal. It is the universe pushing back, asking us to widen our lens, to stop searching only for particles and forces, and start searching for principles. Many physicists now suspect that space and time are not the foundation of reality, but its byproducts. That geometry and gravity may arise from patterns of quantum entanglement, and that the true building blocks of the universe are not things, but relations, interactions, probabilities, information flows. These ideas are speculative, yes, but they are rooted in data, in mathematics, in logic. They offer a path forward when traditional roads reach dead ends. As our theories evolve, so too does our sense of place in the cosmos. For most of history, humans believed they were at the center of the universe, first geographically, then biologically, then temporally. Copernicus displaced the Earth from the center of the solar system. Darwin displaced humanity from the center of life. The Big Bang displaced us from the center of time. And now, the multiverse, simulation theory, and emergent cosmology may displace us from the very concept of uniqueness. But this need not be a source of despair. In fact, it may be the ultimate invitation to maturity. To recognize that our value does not depend on cosmic privilege, but on consciousness itself. That meaning is not granted from above, but forged from within. In a simulated universe, we are still the ones doing the thinking, feeling, discovering. In a multiverse, we are still the ones asking the questions that matter. In an emergent reality, we are not lost, we are awakening. The twist, then, is not that reality is false or hollow, but that it is deeper, more layered, more profoundly strange than we ever imagined. And in that strangeness lies the potential for a new kind of wonder, not the comfort of final answers, but the exhilaration of endless mystery. This twist reframes not only science but the human story. It suggests that consciousness may be not an accident, but a fundamental process, that the universe may not merely allow awareness, but require it. Some thinkers go further, proposing participatory cosmologies, where reality itself is shaped by observation, where quantum potential becomes actuality only when it is perceived. These ideas remain controversial, but they echo ancient intuitions long held by spiritual traditions that the observer and the observed are one, that the universe is not a machine, but a mirror. Perhaps then, the most unexpected twist is not in the stars, but in ourselves. That we, fragile creatures of carbon and thought, are capable of grappling with the fabric of existence. That we can look into the abyss and not only survive, but grow. That we can entertain the most audacious possibilities, not to escape reality, but to understand it more deeply. We may be simulations. We may be bubbles in an infinite foam. We may be neurons in a cosmic brain. But we are also poets, scientists, and dreamers. And it is our capacity to wonder, to ask, to doubt, to imagine that defines us. In the end, the cosmos does not have to be simple to be meaningful. It does not have to be designed for us to inspire us. Whether we are one universe or one of many, whether we are real or rendered, whether space and time are fixed or fluid, we are here, thinking, asking, becoming, and that, in a universe of endless twists, may be the most miraculous twist of all. As cosmology advances into increasingly speculative and ambitious territory, a sobering truth becomes more and more apparent. For every question we've answered, 100 new ones have emerged. We stand at the edge of understanding, not because we are close to final truths, but because we've finally begun to ask the right questions that pierce the veil of the visible, that challenge the architecture of known physics, that force us to grapple with realities beyond what our senses, tools, and even minds were originally shaped to comprehend. And yet, the path forward is neither smooth nor certain. In fact, some of the greatest challenges in the history of science lie directly ahead. These are not just technical hurdles, they are conceptual, methodological, even philosophical. They demand not only better instruments, but deeper patience, more flexible theories, and a willingness to rethink the very essence of what it means to know something. The first and most obvious challenge is technological. While our current telescopes and detectors are marvels of engineering, they are still bound by limitations that prevent us from seeing the full picture of the universe. The observable universe stretches out 46.5 billion light-years in every direction, but that's not because the universe ends there. It's because that's as far as light has had time to travel since the Big Bang. Beyond that horizon may lie vast, uncharted regions that we may never be able to observe directly. Even within the observable universe, we are constrained by the electromagnetic spectrum. Much of the universe is hidden behind veils of dust, or emits radiation in wavelengths that our instruments struggle to detect. Gravitational wave astronomy is still in its infancy. Neutrino astronomy, similarly, has only scratched the surface. Dark matter and dark energy comprising 95% of the universe's content are completely invisible to our current instruments. We know they're there through inference, but we've never directly detected them. To move forward, we will need a new generation of observatories, each designed to peel back another layer of the cosmic onion. Projects like the Nancy Grace Roman Space Telescope, the European Space Agency's Euclid mission, and the Vera C. Rubin Observatory are poised to map the universe's expansion history, trace the distribution of dark matter, and search for clues about the nature of dark energy. But even these efforts may fall short of the precision needed to definitively answer the biggest questions. For instance, distinguishing between different models of dark energy, such as a cosmological constant versus a dynamic field, requires measurements of cosmic acceleration to within a fraction of a percent over vast scales and epochs. That means wider, deeper, more time-sensitive surveys. It means better resolution, higher sensitivity, and more powerful data analysis methods. There is also an urgent need to push beyond the electromagnetic spectrum. Gravitational wave detectors like LIGO and Virgo have already begun to reveal the universe in a completely new way, capturing the ripples in space-time caused by massive collisions. But these detectors are limited to relatively short wavelengths, and their sensitivity is restricted to rare, high-energy events. The next major step is the Laser Interferometer Space Antenna, LISA, a space-based gravitational wave observatory that will be able to detect lower frequency waves from a wider range of sources, including merging supermassive black holes and possibly signals from the early universe. LISA and its successors may open up a new era of gravitational wave cosmology, providing insights into the formation of structure, the behavior of black holes, and even the inflationary epoch that set the stage for all subsequent evolution. Another frontier is the direct detection of dark matter. Despite decades of effort, no one has yet observed dark matter particles in the lab. Theoretical models have proposed a wide range of candidates from weakly interacting massive particles, WIMPs, to axions, to sterile neutrinos, but all have thus far eluded detection. Ongoing and planned experiments like Xenon NT, Lux Zeppelin, and the Axion Dark Matter Experiment are trying to push sensitivity to new levels. But there's always the possibility that dark matter behaves in a way we haven't imagined, interacting so weakly or existing in such a form that we're looking in the wrong place entirely. If direct detection fails, we may need to explore more exotic ideas, such as modifications to gravity, extra dimensions, or hidden sectors of particles and forces that don't interact with the standard model. Each of these ideas brings new challenges and new opportunities for breakthroughs. The quest to unify general relativity with quantum mechanics remains perhaps the most foundational challenge in theoretical physics. We lack a working theory of quantum gravity that is both mathematically consistent and experimentally verified. String theory, loop quantum gravity, and causal dynamical triangulations are just a few of the many approaches under exploration. But without experimental data, it's difficult to choose between them. Theoretical physicists are working to develop testable predictions that could guide future observations, such as potential signatures in the cosmic microwave background, subtle anomalies in black hole behavior, or deviations from the inverse square law of gravity at sub-millimeter scales. One promising idea is that black holes could be the key to unlocking quantum gravity. Hawking radiation, quantum entanglement, and the holographic principle all converge in the extreme environment near a black hole. And many theorists believe that studying these systems more closely could reveal the quantum structure of space-time itself. However, testing these ideas requires both imaginative theory and experimental ingenuity. This is where computational physics and artificial intelligence are beginning to play a transformative role. Simulations of galaxy formation, dark matter distribution, and black hole dynamics are becoming more sophisticated, driven by machine learning algorithms that can detect subtle patterns in vast datasets. AI may help identify weak signals, classify new kinds of cosmic events, or even propose new theoretical models based on complex observational data. But AI is only as good as the data and models it's given, and that returns us to the core limitation. We still don't have enough data from the deep, early universe to decisively test many of our hypotheses. To gather that data, we must think bigger. Ambitious proposals for next-generation missions include massive radio arrays on the far side of the Moon, which would be shielded from Earth's interference and capable of probing the dark ages of the universe before the first stars formed. Other ideas include interstellar probes that could travel beyond the solar system and use gravitational lensing from the Sunday to magnify distant exoplanets or cosmic objects. Still more visionary plans involve building neutrino observatories beneath the Earth's crust or deploying swarms of tiny spacecraft to map gravitational waves from multiple points in space. These projects require not just money, but sustained international collaboration, bold thinking, and long-term vision. They are not merely technical undertakings. They are cultural statements about humanity's desire to know. And yet, technology is only part of the picture. The bigger challenge may be cognitive. Many of the questions we now face lie at the edge of conceptual intelligibility. What does it mean for space-time to be emergent? How do we describe universes with different numbers of dimensions or different laws of logic? What does it mean to observe a universe when the observer is entangled with the system? These are not questions that can be answered solely with equations or telescopes. They require new philosophical tools, new metaphors, new modes of thinking. They require scientists who are willing to explore ambiguity, to accept uncertainty, to live without closure. In this sense, the next great leap in cosmology may be not just technological or theoretical, but epistemological. We must evolve not only our instruments, but our minds. There are also social and institutional challenges. Science today is conducted within systems that reward productivity, safety, and consensus. But cosmology thrives on bold speculation, on interdisciplinary risk, on long-shot ideas that may take decades to bear fruit. We need funding models that support blue-sky thinking. We need education systems that encourage philosophical inquiry, as well as technical mastery. And we need a public that understands science not as a catalog of facts, but as a dynamic, unfolding process of discovery. The unknown is not something to be feared. It is the most human of territories. The next generation of scientists must be trained not only to handle vast datasets and quantum calculations, but to navigate uncertainty, to communicate complexity, and to think across traditional boundaries. They must be storytellers, philosophers, engineers, and explorers all at once, because the cosmos will not yield its secrets to one kind of mind. It will require many, analytic and intuitive, skeptical and imaginative, precise and poetic. And we must prepare ourselves to meet that challenge. The final challenge is existential. As we probe the deep architecture of the universe, we are also probing the nature of ourselves. We are asking questions that blur the line between physics and philosophy, between measurement and meaning. Why is there something rather than nothing? What is consciousness? Is the universe intelligible because it is designed to be, or because we are part of its unfolding logic? These are not questions with simple answers, but they are questions worth asking, because the act of asking changes us. It sharpens our awareness. It deepens our empathy. It expands our sense of time, of space, of possibility. The hurdles ahead are immense, but they are not walls, they are invitations. To build better tools, to form deeper theories, to imagine wilder realities, and above all, to stay curious. Because the greatest discoveries are not the ones that confirm what we expect, they are the ones that surprise us, that humble us, that open doors we never knew existed. And as we continue to explore those doors, we will not only learn more about the cosmos, we'll learn more about what it means to be human, to wonder, to ask, and to reach for the stars not just with our hands, but with our minds. We are nearing a point in scientific history where the most profound questions about the universe may no longer be abstract. Some of them are becoming testable, some are on the edge of technological reach, and others are actively being rewritten by a new generation of theorists. This is the final confrontation, not in the sense of an ending, but in the sense of culmination, the meeting of divergent ideas, competing theories, and irreconcilable frameworks, all converging on the same goal: to understand the true nature of the cosmos. It is a confrontation not between individuals or institutions, but between paradigms, between the physics of the very large and the physics of the very small, between the measurable and the unknowable, between timeless truths and emerging realities. The stakes are nothing less than the fate of science's greatest dream: to unify our understanding of the universe under a single coherent theory. At the heart of this confrontation lies the most persistent rift in modern physics: the division between general relativity and quantum mechanics. General relativity, Einstein's great theory of gravity and spacetime, describes the universe at the largest scales with unmatched precision. It explains the expansion of the universe, the warping of space near black holes, and the behavior of time itself under extreme conditions. But it breaks down at singularities regions like the Big Bang or the center of a black hole, where densities become infinite and space-time curvature becomes undefinable. Quantum mechanics, on the other hand, describes the subatomic world with astonishing accuracy. It governs the behavior of particles, fields, and forces at the smallest scales, embracing uncertainty, entanglement, and non-locality. But it has no built-in concept of gravity. When you try to combine the two, you try to describe a region of space that is both extremely small and extremely dense, mathematics breaks down. The two most successful theories in science are fundamentally incompatible. This is the great fracture at the foundation of physics. In recent decades, several major contenders have emerged to bridge this divide. One of the most ambitious is string theory, which posits that the fundamental constituents of the universe are not particles, but one-dimensional strings vibrating at different frequencies. These strings exist in higher dimensional space, up to 10 or 11 dimensions in some models, and their interactions naturally include gravity. String theory has yielded powerful insights, especially through its duality principles, such as the AD-S-CFT correspondence, which suggest a deep connection between gravity in higher dimensional space and quantum field theories on lower dimensional boundaries. Yet despite its elegance, string theory faces criticism for its lack of testable predictions. It describes a landscape of possible universes more than 10 circumflex 500, making it difficult to pinpoint which, if any, corresponds to our own. For all its mathematical beauty, string theory remains more of a framework than a complete theory. An alternative path is loop quantum gravity, which takes a radically different approach. Instead of adding dimensions or new entities, it attempts to quantize space-time itself. In loop quantum gravity, space is not smooth and continuous, but made of discrete loops woven together into a dynamic network called spin foam. Time, too, may be emergent, arising from the relationships between quantum events. Loop quantum gravity has had success describing the quantum properties of black holes and the Big Bang, suggesting that singularities may be avoided entirely, that spacetime may bounce rather than break. Unlike string theory, it does not unify all the forces, but it may provide a complete theory of quantum spacetime. However, it too remains untested, limited by the challenge of making contact with observable predictions. Meanwhile, other approaches are emerging that reject the premise that space and time are fundamental at all. The holographic principle, already explored through string theory's dualities, suggests that the true description of the universe may be encoded on lower dimensional boundaries. Some physicists believe that spacetime itself emerges from quantum entanglement, that geometry and gravity are byproducts of the structure of quantum information. This, from qubit perspective, championed by researchers like Leonard Susskind and Juan Maldacena, turns the problem inside out. Rather than starting with spacetime and trying to quantize it, it starts with quantum theory and tries to reconstruct spacetime as an emergent phenomenon. These ideas are still in development, but they represent a profound shift in perspective, one that could unify physics not through equations of motion, but through principles of information and computation. And then there are radical ideas, like causal set theory, non-commutative geometry, asymptotically safe gravity, and emergent gravity, all different attempts to describe the quantum structure of space-time. Some suggest that gravity is not a fundamental force, but an entropic or statistical effect, like temperature. Others propose that time is not real, or that the universe is fundamentally computational, a kind of cosmic algorithm running across a network of interacting events. These theories challenge our deepest intuitions, and many remain speculative. But their very existence signals a new phase in the scientific process, the willingness to think beyond traditional categories, to experiment not just with data, but with the foundations of reasoning itself. Amid this theoretical diversity, the question remains: will we ever find a true boundary, a definitive, final theory that explains everything? Some physicists, like Stephen Hawking in his later years, doubted it. They pointed out that nature may not be built on a single, elegant principle, but on a patchwork of overlapping models, each valid within its own domain. Others remain hopeful that a theory of everything is still within reach, perhaps through a yet undiscovered symmetry or principle. But even if such a theory exists, we may face limits to our ability to understand it. The universe may contain elements that are forever beyond our observational reach. There may be physical limits to computation, to measurement, or even to thought. Gödel's incompleteness theorems, Heisenberg's uncertainty principle, and the cosmic horizon itself all hint at boundaries not just in space, but in knowledge. Still, the pursuit continues, because the act of asking is itself transformative, because every attempt to unify our understanding refines our methods, deepens our humility, and expands our imagination. The future of cosmology is not just about solving equation sets, about constructing new languages, new philosophies, new technologies, and new ways of seeing. Already, next-generation instruments are poised to revolutionize the field. The James Webb Space Telescope, the Vera Rubin Observatory, LISA, and future quantum observatories will collect data with unprecedented precision, probing the earliest moments of the universe, the nature of dark matter, and the behavior of gravity in extreme environments. Meanwhile, advances in quantum computing, machine learning, and AI will enable theorists to simulate models that were once unimaginable, exploring the mathematical landscape of reality with tools that blur the line between human and machine reasoning. In the coming decades, we may detect signatures of quantum gravity. We may uncover the nature of dark energy. We may find evidence for extra dimensions or signs that space-time itself is discretized. We may observe gravitational waves from the inflationary epoch or anomalies in the cosmic microwave background that confirm or refute our deepest theories. Or we may not. The data may remain stubbornly ambiguous. The theories may proliferate faster than they converge. The universe may remain, in some fundamental way, unknowable. But in that unknowability lies a different kind of truth. Not the closure of final answers, but the openness of perpetual discovery. Not a map with all the borders drawn, but a living process of exploration, where the edge is not a boundary, but a frontier. The final confrontation is not between one theory and another. It is between certainty and wonder, between completeness and curiosity. And in that confrontation, we find not the end of science, but its renewal. The future of cosmology will not be about finality. It will be about participation, about asking deeper questions, embracing more radical ideas, and creating more powerful tools. It will be about connecting disciplines, merging physics with philosophy, mathematics with metaphysics, and observation with imagination. It will be about building a science that is as complex, as layered, and as beautiful as the universe it seeks to describe. And perhaps, in doing so, we will find a new kind of boundary knot, a wall that limits us, but a mirror that reflects us, a boundary that shows us who we are, where we come from, and what we are capable of becoming, a boundary that is not the end of knowledge, but the beginning of wisdom. In a universe so vast that it stretches comprehension, in which light takes billions of years just to cross a single corner, and in which even our most powerful tools reveal only a sliver of what exists, one might be tempted to ask, why bother? Why do we explore the cosmos? Why pour time, energy, and imagination into understanding something so distant, so indifferent, so unreachable? Yet this question, rather than diminishing the effort, illuminates its deepest meaning. The exploration of the unknown is not merely a scientific endeavor, it is a moral one. It reflects the best of what it means to be human, the refusal to accept ignorance as our fate, the audacity to question everything, and the quiet, persistent belief that there is something worth discovering, even in the face of cosmic silence. The moral takeaway of our journey into the stars is not a technical conclusion, it is a transformation of perspective. It teaches us how to live, how to think, and what it means to belong to a universe that is, by every measure, beyond us. At the heart of this journey lies curiosity, raw, powerful, and endlessly generative. Curiosity is the engine of science, but it is also the soul of progress, the thread that connects childhood wonder to adult innovation, myth to mathematics, art to equation. It is curiosity that drove early humans to track the stars with stones and to align monuments with celestial cycles. It is curiosity that guided Galileo's telescope to the moons of Jupiter, that inspired Newton to ask why the apple fell, and that urged Einstein to imagine riding alongside a beam of light. It is curiosity that asks not just what is it, but what does it mean? And what else might be true? In this way, curiosity is not merely a tool, it is a value, a stance, a way of engaging with reality that privileges questions over dogma, exploration over complacency, and humility over control. This humility is essential. The cosmos does not answer easily. Every revelation seems to generate more mystery. We learn that the Earth is not the center of the universe, but a speck in a vast, expanding field. We learn that matter itself is mostly empty space, held together by invisible forces. We learned that 95% of the universe is made of dark matter and dark inner substances we cannot see or touch. Each of these discoveries should have shattered human arrogance, and in many ways, they did. But they also did something else. They expanded our sense of beauty, of depth, of possibility. To look into the void and not flinch, to embrace mystery as the natural state of things, is not an act of despair, it is an act of courage. It is a declaration that the unknown is not our enemy, but our inheritance. In this balance between knowledge and mystery lies one of the deepest lessons of cosmic exploration. We do not seek to replace wonder with certainty. We seek to deepen wonder through understanding. Science, at its best, does not close the door on mystery, it opens it wider. Each discovery, a new exoplanet, a quasar, a gravitational wave, is not the end of a story, but the beginning of a new one. In this sense, science and spirituality are not opposites. They are parallel expressions of the same longing to connect, to comprehend, to transcend the boundaries of the immediate. The nebulae and galaxies captured by telescopes are not just data, they are visions of the sublime, reminders that we are part of something infinitely larger than ourselves, and yet intimately connected to it. This perspective shift has moral implications. When we understand that we are stardust literally forged in the hearts of ancient stars, we begin to see ourselves differently. We are not separate from the cosmos, nor above it, but expressions of it. Our thoughts, our cities, our dreams, they are the universe becoming aware of itself. This awareness should engender reverence, not superiority. It should inspire stewardship, not exploitation. It reminds us that Earth is not just a resource, it is a rarity, a haven of complexity and life in an otherwise cold and indifferent universe. Protecting it becomes not just an environmental duty, but a cosmic one. We may be the only species capable of even asking these questions, and that makes us responsible not only for ourselves, but for the future of consciousness in the universe. Moreover, cosmic exploration reminds us of our unity. The divisions we cling to, borders, ideologies, hierarchies, shrink under the weight of the stars. From space, there are no nations. There is only Earth, blue, delicate, alive. The overview effect, experienced by astronauts, is a profound psychological shift brought on by seeing Earth from orbit. It instills a sense of interconnectedness, a clarity about what matters. But we need not travel to space to feel it. We can cultivate that perspective through science, through storytelling, through education. The more we understand the universe, the more we see that our differences are superficial and our commonality is fundamental. We are all bound by gravity, by biology, by time. We are all moving through the same cosmos, subject to the same physical laws, illuminated by the same ancient light. This insight has the power to transform human behavior. It can make us more patient, more collaborative, more farsighted. It can shift our priorities from conquest to cooperation, from consumption to sustainability, from isolation to connection. Cosmic exploration reminds us that short-term thinking is a luxury we can no longer afford. The universe is vast, but the biosphere is fragile. Our time here is limited, but our impact is lasting. We must ask ourselves, what kind of species do we want to be? One that burns bright and self-destructs, or one that learns to live wisely, to listen deeply, and to grow beyond its origins? To ask such questions is itself a form of growth. It shows that science is not just about technology, it is about wisdom. It is about expanding our capacity to care, to understand, to imagine. And it is about building a future that honors the past without being bound by it. The tools we use to measure the stars, telescopes, the satellites, the simulations are also tools for measuring ourselves. They show us what we value, what we fear, what we hope for. They are mirrors as much as they are windows, and the reflection they offer is complex. We are capable of great beauty and terrible harm. We launch golden records into the void while poisoning our oceans. We dream of other worlds while neglecting our own. We reach for the stars while struggling to understand each other. But perhaps this tension is part of the journey. Perhaps the moral growth that cosmic exploration invites is not about perfection, but about becoming more conscious of our contradictions and choosing to transcend them. To look into the universe is to look into a paradox. Infinite silence filled with meaning, eternal cold lit by fire, emptiness that gives birth to everything. In confronting that paradox, we are forced to become more than we were. So what, ultimately, is the moral takeaway of exploring the unknown? It is this: that the pursuit of knowledge is not separate from the pursuit of meaning, that curiosity is a sacred impulse, that the unknown is not a void to be feared, but a womb of possibility, and that by venturing into it with courage, humility, and wonder we do not diminish ourselves. We become more fully human. We become participants in a story far greater than our own, one that began long before we were born and will continue long after we are gone. And yet, in this moment, we are here, thinking, asking, creating, and that, in a universe of infinite mystery, is an act of extraordinary grace. We may never find all the answers. We may never see the edge, but the questions, the willingness to ask them, to follow them wherever they lead are enough. They are the fire that lights the mind, the compass that guides the heart, the bridge that connects us to each other and to the cosmos. In this search, there is purpose. In this wonder, there is truth. And in this mystery, there is something deeply, quietly, eternally beautiful. The human spirit, reaching out into the dark and finding not just stars, but itself. After all the theories have been weighed, after the data has been parsed, and the models debated, we come to the final page of our cosmic inquiry with a question that is not mathematical, but philosophical. Should the mystery remain open-ended? Should we keep seeking a final answer to the nature of the universe? Or is the value of the cosmos not in its resolution, but in its vast, unbounded potential to forever challenge, inspire, and humble us? This is not just a question for physicists. It is a question for humanity. We are the only species, as far as we know, that looks up at the stars not just with eyes, but with questions. And as we reflect on all we have explored from the earliest light of the universe to the deepest voids of intergalactic space, we are faced with the profound possibility that the greatest gift of cosmic exploration is not knowledge, but mystery itself. To leave a question unanswered is not to fail. It is to recognize that the value of a question may not lie in its answer, but in the journey it demands. The deepest truths about the universe may not be conclusions we reach, but perspectives we earn through inquiry. Consider the history of science. Every breakthrough led not to closure, but to greater openness. Newton gave us deterministic laws, and Einstein shattered them with relativity. Quantum mechanics revealed a universe governed by uncertainty, entanglement, and probability. The discovery of dark energy shattered the notion of a static cosmos and replaced it with one that is not only expanding, but accelerating. The cosmic microwave background didn't tie off our understanding of the Big Bang, it exposed new puzzles in its subtle anisotropies. The more we learn, the more we realize how much we do not know. We have mapped only a tiny fraction of the observable universe. We have no access to what lies beyond it, no evidence of what preceded the Big Bang, and no consensus on how to unite the laws that govern the large and the small. These are not gaps in knowledge, they are the engines of progress. An open-ended mystery invites perpetual curiosity. It prevents stagnation. It pushes scientists to refine their models, philosophers to deepen their inquiries, artists to expand their metaphors. If we had all the answers, if there were no unknowns left, would we even bother to explore? Would we build observatories, launch satellites, theorize universes beyond our own? The unknown fuels our imagination. It forces us to admit the limitations of our tools and our minds, but it also invites us to transcend them, to ask whether space and time are fundamental, whether consciousness plays a role in observation, whether reality is information, geometry, or something else entirely, and to do so not from despair, but from awe. We do not need to resolve the mystery to be changed by it. The mystery itself is transformative. This, perhaps, is the most enduring lesson from our exploration of the cosmos. Not a list of facts, but a shift in awareness. The universe is not a fixed object waiting to be explained. It is a living question that demands to be engaged. It is a mirror that reflects our deepest hopes, our sharpest doubts, our longing for meaning in an indifferent void. And yet, in that indifference, we find something deeply beautiful. We find that meaning is not given, it is made. We make it by wondering, by searching, by never being content with easy answers, by choosing to live in the tension between what we know and what we cannot yet grasp. Among the biggest takeaways of our cosmic journey is the realization that we are not at the center, not of space, not of time, not of anything. And yet, we matter not because the universe is designed for us, but because we are capable of understanding it. Because we are composed of the same elements forged in stars, the same particles shaped by cosmic forces. Because we are the universe, contemplating itself. We are entropy's exception, a moment of order and awareness, fleeting and improbable, yet filled with insight. That insight shows us that the universe is not empty, it is full of structure. Galaxies form filaments, black holes collide in dances of space-time, quantum fields ripple with possibility. It shows us that everything is connected, from the spin of an electron to the rotation of a galaxy. And it shows us that our search is not in vain. Every step we take into the unknown, every equation, every observation, every question asked, deepens our place in the universe. We have explored theories of everything, from string theory to loop quantum gravity. We've examined the strange elegance of the holographic principle, the unsettling possibility of the multiverse, and the speculative challenge of the simulation hypothesis. We've pondered the reality of dark matter and the accelerating expansion caused by dark energy. We've watched time bend, space twist, and particles behave like waves. Each concept stretches the boundaries of what we thought we understood, and each invites us to rethink what counts as real. Yet despite their differences, all these ideas share a single theme. The universe is more mysterious than we imagined, and more knowable than we deserve. We've also come to understand the moral weight of this exploration. That science is not just a method, but a mirror. That the questions we ask shape the kind of society we build. That cosmic exploration teaches humility, resilience, and empathy. That when we see the Earth from afar as a pale blue dot adrift in a sea of darkness, we begin to grasp both our insignificance and our responsibility. We may be tiny, but we are not meaningless. We may be fragile, but we are capable of launching probes to other planets, of listening to whispers from the edge of time, of asking whether we are alone or not, just biologically, but existentially. And so we come to the final thought, not a conclusion, but a continuation. The mystery should remain open, not because answers are unreachable, but because reaching for them is the point. The universe is not a problem to be solved. It is a relationship to be cultivated. We do not stand apart from it, we are in it, of it, moving through it. Its rhythms shape our biology, its particles build our bodies, its light defines our vision. To explore it is to return home, not to a physical place, but to a deeper understanding of where we belong. In every galaxy, every quasar, every black hole and gravitational wave, there is a message not in language, but in structure. Keep going, keep asking, keep reaching. The edge is not a limit, it is a horizon. And as long as we have the courage to move toward it, the story continues. A story not of endings, but of ever-widening perspectives, of new ways to think, to feel, to see, of questions not yet asked, and discoveries not yet dreamed. So should the mystery remain open-ended? Absolutely. Not as a failure of science, but as its triumph. The openness of the universe is not a gap in our understanding, it is the space where understanding begins. It is the canvas for our imagination, the arena for our growth, the playground of our highest thought. And in that openness, we do not find emptiness, we find possibility. Infinite, eternal, breathtaking possibility. And that is enough. That is everything.